Ever stared out of a car window, feeling like the world outside is rushing past you, even though you're sitting perfectly still? Or maybe you've tripped over something seemingly insignificant on the floor, your body continuing forward while your foot suddenly stops. These everyday experiences, seemingly simple, hold a profound secret about the very nature of motion, a secret first articulated by one of history's greatest scientific minds, Sir Isaac Newton. But before we dive deep into the fascinating world of Newton's first law, let's ponder this: what does it truly mean for something to move? We often think of movement as a change in position, which is certainly part of it. But what causes that change? And what happens when nothing is causing a change? This is where the brilliance of Newton's first law, also known as the law of inertia, truly shines. It's not just about things moving, it's about why they keep moving, or why they stay still in the first place. Think about a perfectly smooth ice rink. If you give a hockey puck a push, it will slide across the ice for a considerable distance, seemingly without slowing down much. Now imagine doing the same on a rough patch of asphalt. The puck would stop much sooner. What's the difference? Friction. The ice offers very little resistance to the puck's motion, while the asphalt creates a significant opposing force. Newton's genius was to imagine a scenario where this resistance, this friction, was completely absent. What would happen then? His answer, elegantly simple yet incredibly powerful, forms the core of his first law: an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. Let's break that down. The first part is fairly intuitive. A book sitting on a table isn't going to suddenly leap into the air on its own. It will remain at rest unless someone picks it up or pushes it. The second part, however, might seem a little less obvious in our everyday experience. We rarely see things moving indefinitely at a constant speed and direction without any apparent force acting on them. That's because, in our everyday world, forces like friction, air resistance, and gravity are almost always at play. But these forces don't invalidate Newton's first law, they actually highlight its importance. They are the unbalanced forces that cause objects to change their state of motion, to speed up, slow down, or change direction. Newton's first law tells us what would happen in the absence of these forces, providing a fundamental baseline for understanding how forces affect motion. So, now that we have a solid grasp of the core principle, let's explore 5 compelling examples that illustrate Newton's first law in action, some in obvious ways and others in ways you might not have considered. These examples will not only solidify your understanding but also reveal how this seemingly simple law governs much of the world around us. Example 1. The magic trick and the reality of inertia. Imagine a classic magic trick. A tablecloth is swiftly pulled from under a table full of dishes, and miraculously, the dishes remain in place. It looks like magic, but it's a beautiful demonstration of inertia. The dishes, at rest, have a tendency to remain at rest. When the tablecloth is pulled quickly, the force of friction acting between the cloth and the dishes is minimal and acts for a very short duration. This brief, small force is not enough to overcome the inertia of the dishes, their inherent resistance to changes in their state of motion. As a result, they stay put, seemingly defying gravity for a fleeting moment. Think about what would happen if you tried to pull the tablecloth slowly. In that case, the friction between the cloth and the dishes would act for a longer period, exerting a greater force that would likely cause the dishes to move along with the cloth, perhaps even topple over. The quickness of the pull is crucial to minimizing the impact of the unbalanced force, friction, and allowing inertia to dominate. This seemingly simple trick beautifully illustrates the first part of Newton's law: an object at rest tends to stay at rest. Example 2. The never-ending journey in space. Now, let's venture beyond our earthly experiences and consider the vast emptiness of space. Imagine a spacecraft traveling through deep space, far away from any significant gravitational influence or atmospheric drag. Once the spacecraft's engines are shut off, what happens to its motion? According to Newton's first law, it will continue to travel in a straight line at a constant speed. There are no significant unbalanced forces acting on it to slow it down or change its direction. This is precisely how spacecraft navigate the cosmos. Engineers use short bursts of engine power to adjust their trajectory and speed, and then, for vast stretches of their journey, the spacecraft simply coasts through space, relying on its inertia to carry it forward. This principle not only saves fuel but also highlights the profound implications of Newton's first law in an environment where friction and air resistance are virtually absent. It's a real-world example of an object in motion staying in motion with the same speed and in the same direction because there's no unbalanced force to stop it. Example 3. The sudden stop and the flying passenger. We've all experienced this, perhaps a little too abruptly. You're riding in a car that suddenly slams on the brakes. Your body, however, seems to continue moving forward, potentially even lurching towards the dashboard or the seat in front of you. This is another direct consequence of inertia. Your body, in motion with the car, has a tendency to remain in motion at that same speed and in the same direction. When the car decelerates rapidly due to the braking force, your body continues its forward motion until an external force, like the seatbelt or the dashboard, hopefully avoided, acts upon it to bring it to a stop. This example powerfully illustrates the importance of safety features like seatbelts. Seatbelts provide the necessary unbalanced force to counteract your body's inertia in the event of a sudden stop, preventing potentially serious injuries. The feeling of being thrown forward isn't some mysterious force acting on you, it's simply your body continuing its original motion according to Newton's first law until another force intervenes. Example 4. The dust cloud that lingers. Think about a cloud of dust kicked up by a passing car or a gust of wind. You'll notice that even after the car has driven away or the wind has died down, the dust particles remain suspended in the air for a while, gradually settling down. This lingering effect is, in part, due to inertia. The dust particles, once set in motion by the car or the wind, tend to continue moving in that direction. Of course, gravity will eventually pull them down, and air resistance will slow their horizontal motion. However, initially, their inertia keeps them suspended and moving. The smaller the dust particles, the less significant the force of gravity relative to their inertia, and the longer they tend to stay aloft. This everyday phenomenon, from dust clouds to smoke plumes, showcases how objects in motion resist changes to their state of motion. With that said, thanks for watching and until next time.